Hi guys, I'm Mr. Joseph, your chemistry teacher. So today's lecture is a continuation of our previous lecture on entropy change. So the lesson objectives for today, we are going to define the term entropy as the number of possible arrangements of particles and their energy in a given system. Then we are going to predict and explain the sign of the entropy change that occurs during a chemical reaction in which there is a change in the number of gaseous molecules. Then we'll look at how we can calculate the entropy change for a reaction, given the standard entropies of the reactant and the products. So we'll be talking about the entropy of the system. So please, I want us to listen attentively and get the best out of today's lecture. So we're looking at entropy changes in reactions. Now, when considering the entropy change in a chemical reaction, we can examine the entropies of the reactant and the products. So it is important to note whether the entropy increases or decreases. Now, generally, gases have higher entropy value, while solids have low entropy value. So if there's a difference in the number of gas molecules involved in the reaction, there will likely be a significant change in entropy. So this is due to the fact that gases have high entropy values. The more the gas molecules there are, the greater the number of ways they can be arranged, resulting in a higher entropy. So when there's an increase in the number of gas molecules, there's an increase in entropy. When there's a decrease in the number of gas molecules, there's a decrease in entropy. That is from reactant to product or product to reactant. So we have to consider that in reactions. So that's what we're talking about, entropy changes in reactions. So we can use the changes in the number of gas molecules in chemical reaction to tell if there's an increase or decrease in entropy. So if there are more number of gas molecules on the product, that means there's an increase in entropy. If there's less number of gas molecules on the product, there's a decrease in what? Entropy. So we want to look at how changes in the number of gas molecules, how we can use changes in the number of gas molecules to predict whether there's an increase or decrease in entropy. Now, if you look at the reaction, for example, the reaction before us is thermal decomposition of calcium carbonate, which is solid, to give you calcium oxide solid and carbon dioxide, which is a gas. So what happens? There's an increase in the entropy of the system because a gas is produced, which is high entropy. But the reactant, calcium carbonate, which is a solid, entropy is low. So in general, there's an increase in what? In entropy, because there's an increase in the number of gas molecules on the product. Now, look, the second example is the manufacture of ammonia, where nitrogen reacts with hydrogen to give you what? Ammonia. So on the reactant, we have four moles of gases, while on the product we have 2 moles of gases. So there's a decrease in the number of gas molecules on the side of the product. So we should expect a decrease in the entropy of the system because there's a reduction in the number of gas molecules as the reaction proceeds. So the entropy change of the system is negative. So the reactants, hydrogen and nitrogen, are more stable than the product, which is what? Ammonia. So on the reactant, there's an increase in entropy. Entropy change is positive, while on the product, there's a decrease in entropy. Entropy change is what? Negative. So with the number of gas molecules in chemical reactions, we can tell if there's an increase or decrease in entropy, or if the entropy value is positive, or if the entropy value is what? Negative. That means when there's an increase or there's what? A decrease. So this is a typical examination question before us. So let's consider it. What is the sign of the entropy change in the following reactions? So you have to give reasons for your decision. So if you look at the first one, thermal decomposition of calcium carbonate to give you calcium oxide, which is solid, and carbon dioxide gas. So there's an increase in entropy. So entropy change is what? Positive, because there's an increase in the number of gas molecules. So there's an increase in entropy. Then the next one is formation of ammonium chloride, which is solid. So there's entropy change is negative. There's a decrease in entropy because there's a change from what? Gas to what? Solid. So there's a change from gas to solid. So there's a decrease in what? Entropy. Then C is solid to what? Gas. So there's an increase in what? Entropy. There's a change from solid to gas. So entropy change what? Increase. That means there's increase in the number of gas molecules. Then if you look at D, entropy change is what? Positive, because on the reactants you have 9 moles of gas, while on the product you have 12 moles of what? Gases. So there's an increase in the number of gas molecules. Then E, the entropy change is neither positive nor negative. It is, we can say the entropy change is 0 here, because there's the number of moles of gas, there are equal number of moles of gas on the reactant and also on the product. So the entropy is neither positive nor negative. So the entropy change delta S is equal to what? 0, where you have equal number of moles of gases on both sides of the reactant and also on the products. So we're looking at entropy change of the system. So we'll talk about the system. The system is the part that is under investigation. That is, the system has to do with the reactant and the product. So entropy values can be used to predict whether a chemical reaction will occur spontaneously or not. But when chemical reactions occur, entropy changes occur because the reactant and product have different entropy values. So for the system, that has to do with the reactant and product. The entropy change of the system will be equal to what? Entropy change of the product minus that of the reactant. So to get the entropy change of the system, it has to do with entropy change of the product minus the standard entropy change of the reactant. So that's how you get the entropy change of the system. So we are looking at the entropy change of the system and how we can calculate the entropy change of the system. So we'll talk about the system is the part that is under investigation. So we're referring to the reactant and to the product. So in calculating the entropy change of the system, what happens? We have to take into account what? The reactant and the product. So in order to calculate the entropy change of the system, we use the relationship that entropy change of the system, we use the standard molar entropy value, which is the standard entropy value. Standard entropy change of the system is equal to the standard entropy change of the products minus the standard entropy change of the reactant. So that is how we calculate what? The standard entropy change of the system. So we need to take note of this, that we need to take account of the stoichiometry of the equation. Yes, while calculating the entropy change of the system, we need to take account of the stoichiometry of the equation, the stoichiometry of the products and the stoichiometry of the reactant. And also when looking up entropy values in tables of data, we need to choose the data for the correct state, solid, liquid, or gas. Like water can be in solid state, it can be in liquid state, it can be in gaseous state. So we need to take account, we need to look out for the correct data so that we can get the correct answer while trying to carry out calculation. So standard entropy change of the system is equal to the standard entropy change of the products minus the standard entropy change of the reactant. So please let's take this because we are going to apply them in solving problems. So this is a typical example for us to look at. So you are asked calculate the entropy change of reaction for the reaction below. So you are given the reaction with 2 moles of nitrogen oxide plus oxygen to give you 2 moles of nitrogen oxide. You are provided with the standard entropies in table 2. So you are asked to calculate the entropy change of the system, standard entropy change of the system. As we all know, standard entropy change of the system is equal to what? Standard entropy change of the system, which is called the summation of the standard entropy change of the products minus the standard entropy change of the reactant. Please, we need to take account of what the stoichiometry while trying to calculate. So the product is what? Nitrogen oxide. So summation of what? 2 times what? Standard entropy change of nitrogen oxide minus what? Summation of what? 2 times standard entropy change of nitrogen oxide and what? Standard entropy change of oxygen. So you can see that we'll put the stoichiometry into consideration. Please, I want us to take note of that so you get the right answer. So the standard entropy change of the system will be equal to 2 times 240 minus 2 times 211 plus 205. So the standard entropy change value is equal to minus 147 joule per Kelvin per mole. So as you can see, it's as simple as what? As ABC. All you just need to do is to apply the formula. The standard entropy of the system is equal to the summation of the standard entropy change of the products minus the summation of the standard entropy change of the reactant. Please don't forget to consider the stoichiometry of each of the reactant and the product so that you can apply it very, very well in your calculation. So it's as simple as A, B, C. Please just attempt as many questions as possible and you can see how simple it is. So this is a tag before us, which is a typical examination question. So I just want us to solve it together. So the question goes, silicon is purified by first heating it in a stream of hydrogen chloride gas to form silicon hydrogen trichloride. Then the silicon hydrogen trichloride form is then distilled to remove other impurities. So the reaction is here. So table 2.1 shows some standard entropy data. Use the data in table 2.1 to calculate the standard entropy for reaction 2. So applying our formula, to calculate the standard entropy change of the system. Standard entropy change of the system is equal to summation of standard entropy change of the products minus summation of standard entropy change of the reactants. So the entropy change of the system, the standard entropy change of the system, is equal to the product is silicon hydrogen trichloride, which is 314, plus hydrogen gas. Hydrogen gas is 131, minus the reactant, which is silicon. Silicon is 19, plus hydrogen chloride gas, which is 3 times that of hydrogen chloride gas, which is 3 times 187. 87. So I'm to use my calculator. So 314 plus 131. 314 plus 131, you have 445 minus, I'm using a calculator, 19 plus 3 times 187. So you have 580. So if you have to subtract 455 minus 580, you have minus 135. So the answer is what? Minus 135 joule per Kelvin per mole. So you can see it's as simple as ABC. All you just need to do is to apply the formula, which is entropy of the system is equal to entropy of the product minus reactant. And also you take into account the stoichiometry of the reactant and that of the product. So it's as simple as ABC. So please solve as many questions as possible. Attempt as many questions. Feel free to reach out to me if you encounter any difficulty. So we're looking at the entropy change of the surroundings. So we'll talk about the surroundings. We're referring to our environment. The surroundings include the apparatus we use, the air around us. Even you yourself, you are part of the surrounding. So during chemical reaction, heat is either released from the system to the surrounding or from the surrounding to the system. So we have to talk about the entropy change of the surroundings, because many chemical reactions are accompanied by large entropy change. And during chemical reactions, heat is released, either it is released to the surrounding or heat is absorbed from the surrounding. Heat is either released from the system to the surrounding or from the surrounding to the system. So this entropy changes the number of ways of arranging the energy in the surroundings. So in many chemical reactions, the value of the entropy changes in the surrounding cannot be ignored. Yes, it's very, very important. It cannot be ignored because heat is usually released from the system to the surrounding to the system. That is vice versa. So the entropy change of the surrounding is calculated using the relationship. So entropy change of the surrounding will give you entropy change of the surrounding will be equal to what? Entropy of the reaction divided by what? The temperature, which is temperature is Kelvin. Where delta H reaction is the standard entropy change of the reaction, and T is the temperature in Kelvin. As standard temperature, this value is what? 298 Kelvin, which is 25 degrees Celsius under standard conditions. That is at a standard temperature. So the value is 298 Kelvin. So we need to consider that. So to calculate the entropy change of the surrounding, entropy change of the surrounding will be equal to what? The negative minus entropy change of the reaction over divided by what? Temperature. The negative sign is part of the equation. The negative sign is part of the equation. It's not for the entropy change of the reaction. The entropy change of the reaction can be positive or negative depending whether it is exothermic or endothermic. So we have to consider the entropy change of the reaction. So with this formula, we can calculate the entropy change of the surrounding. So this is a typical examination question before us. This is an example. So let's look at this. Calculate the entropy change of the surrounding for the reaction. So this is the reaction: 2 moles of calcium react with 1 mole of oxygen to give you 2 moles of calcium oxide, and you are given the entropy change of the reaction, which is minus 1270.2 kilojoule per mole. So the first thing we need to do is to convert the entropy change into joule per mole by multiplying by 1000. So to convert it to joule per mole, you multiply by 1000 to give you minus 1270.200 joule per mole. So if we apply the entropy change of the surrounding, entropy change of the surrounding is equal to what? Entropy of the reaction divided by the temperature. So I told you that the negative sign is part of the equation, so which is minus minus 1270200 divided by what? 298 Kelvin. So the answer is what? Plus 4262.4 joule per Kelvin what, per mole. So as you can see, it's as simple as ABC. All you just need to do is to apply the formula and put in the values and you get the right answer. So the standard entropy change of the surrounding is 4262.4 joule per Kelvin per mole. So it's as simple as ABC. So please don't forget, whenever you are doing the calculation, the entropy of reaction is usually kilojoule per mole. So you have to convert it to joule per mole by multiplying by 1000, and the negative sign also, you have to put the negative sign into consideration. Minus times minus is equal to what? It's equal to plus. So please take note of that. So these are typical examination questions. This is a task for us to attempt based on what we solve. So you are asked to calculate the entropy of the surrounding in each of the following reactions. Assume that the value of the enthalpy change does not change with temperature. So you are given the enthalpy change of the reaction, then you are given the temperature, so you have to calculate the entropy of the surrounding. So it's as simple as ABC. All you just need to do is to apply the formula and solve, the calculations. So I want you to attempt this task and solve as many questions as possible. And feel free to reach out to me if you encounter any difficulty. Please, in your calculation, don't forget to convert your temperature in degrees Celsius to Kelvin. And also don't forget to convert your enthalpy of reaction to joule per mole, from kilojoule per mole to joule per mole. All you need to do is just to multiply by 1000. And I want you to take note of the fact that in the equation, the negative sign is part of the equation. Enthalpy change of surroundings equals to minus enthalpy change of reaction over temperature. So please take note of that. So please attempt this question and solve as many questions as possible. Reach out to me for any difficulty. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. So attempt this question. So now I want to look at the total entropy. When we talk about total entropy, it has to do with the entropy of the system and also the entropy of the surrounding. So the total entropy change involves both the system and the surrounding. So for the system, it has to do with the reactant and the product. So that is why we say entropy of the system is equal to what? Standard entropy change of the product minus that of the reactant. Now for the surrounding, the entropy change of the surrounding has to do with what? Entropy change of the surrounding. Entropy change of the surrounding is equal to entropy of reaction divided by what? Temperature. So for the total entropy will now be equal to entropy of the system plus what? Entropy of the surrounding. So the total entropy is the sum of the entropy of the system and that of what? That of the surrounding. So because it has to do with the system and the surrounding. So the total entropy now be equal to entropy of system minus entropy of reaction divided by temperature. So if I have to substitute it into this equation, we get total entropy is equal to entropy of the system minus the entropy of the reaction divided by the temperature. Now, if the total entropy change increases, the entropy change is positive. The reaction will then occur spontaneously. The reaction is likely to occur. We said that the reaction is feasible. But if the total entropy change decreases, the entropy change is negative, and the reaction is then not likely to occur. So with the reaction, we say the reaction is not what? Feasible. So with the help of the total entropy, which is the sum of the entropy change of the system and the surrounding, we can tell if a reaction is likely to occur or not likely to what? Occur. It has to do with the total entropy. Then we'll talk about the entropy of the system and also the entropy of the surrounding. So here's an example for us to consider. It's a typical examination question. So let's look at the question. You are asked to calculate the total entropy change for the reaction. You are giving the reaction. This is calcium. You are giving calcium plus oxygen to give a calcium oxide. So you are asked to calculate the total entropy change. And you know total entropy change is equal to entropy change of the system plus entropy change of what? The surrounding. So this is the formula we have to use. The entropy change of the system is this. And you are given the entropy change of the surrounding, which is this. So you have to calculate the total entropy. The total entropy now be equal to entropy of the system plus entropy of the surrounding. So the total entropy is equal to plus 4054.0 joule per Kelvin per mole. So from the value we've gotten, it gives us a large positive value, which indicates that there's an increase in what? Entropy. That means the reaction is likely to occur, that the reaction is feasible because of the increase in entropy, and the entropy, the value of the total entropy is positive. So there's an increase in entropy, and that means the reaction is feasible, the reaction is likely to occur. From the above worked example, so you can see that the large positive entropy change of the surrounding has more than compensated for the negative entropy change of the system. So if you look at the example above, you discover that the entropy change of the system is negative, but the entropy change of the surrounding has a large positive value. So the large positive value has more than compensated for the negative entropy change of the system. So the total entropy change is positive and the reaction is feasible. So from all we've treated, this is a task for us to attempt. Please, I want you to attempt these questions and feel free to reach out to me if you encounter any difficulty and solve as many questions as possible. Please subscribe to my YouTube channel, like, share, and reach out to me if you encounter any difficulty while trying to solve this question. Now, the question says calculate the total standard entropy change in each of the following reactions using the standard molar entropy values given here. So you are using the standard molar entropy values. These are values that are measured under standard conditions. So they are measured at a pressure of 100 kilopascal, a temperature of 298 Kelvin or 25 degrees Celsius. So what happened is that we have to calculate the total entropy. You are given the entropy of the reaction. The temperature is 298 Kelvin because it's under standard conditions, and you are given the value of the entropy. So you have to calculate the entropy of the system, which is the entropy of the product minus the entropy of the reactant. Then you have the temperature and you have the entropy of the reaction. So please attempt these questions and feel free to reach out to me if you encounter any difficulty. I'm Mr. Joseph, your chemistry teacher. Please don't forget to subscribe to my YouTube channel. Don't forget to like, don't forget to share, and reach out to me if you encounter any difficulty. I'm Mr. Joseph, your chemistry teacher. Thank you for listening. Once more, I'm Mr. Joseph, your chemistry teacher. Thank you for listening. Subscribe to my YouTube channel, like, share, and reach out to me if you encounter any difficulty. I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel, Mr. Joe, your chemistry teacher.